Okay, so I want to pick back up where we were yesterday. We had just kind of started an introduction of looking at chapter 8 here and thinking about that fundamental counting principle of like that multiplication that happens. So here's a question I want you to kind of consider as we get started today. How many ways can a 6-question true-false test be answered? Okay. So we'll do that second one here together. I'll just space that down. Let's just kind of think about this first one. So how many ways? Remember, ways is going to be kind of the key phrase here as we look at this. So how would you decide how many ways a 6-question test can be answered? Strategies include things like tree diagrams, right? We've seen that before. You can probably reason it through really quickly and get a result. And what calculation are we doing? 2 to the 6th. So when we think about 2 to the 6th, and that, so 64, right? So what if so yesterday we were talking about like writing like these like blanks out, and sometimes that'll be an easier, like I'm just showing strategy here, so when we think about some other problems, like things that will carry us forward. So when you think about the first question, how many ways can you answer the first question? 2. How many ways can we answer this question? 2, and so on. So maybe something to consider, like maybe you thought about it, maybe you didn't, but is the responses for the questions independent events? So like, does answering true on the first question change how we would answer the second in any way? Right? They're independent, right? So that means it should just be the multiplication. So just 6 2's multiplied together, 2 to the 6th. If you thought of a tree diagram, I'm not going to write the whole thing out, but this is going to help us as we say something different here in a minute. So if I just write out like the first 3 questions, right? So the first question you could answer true, the second one you could answer false, then the third one you could answer true, right? You can follow the path of this tree diagram. So what I want to say is this, that any of the 2 choices here for the third question, right? Any of the 2 choices that correspond to the third question can be paired with any of these 4 choices that have happened. Let me say that again. These 2 choices here, this true-false choice for that third question, aren't we pairing it with any of these 4 outcomes that could have happened of true, 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 false, false, true, false, false, right? So there's something about that multiplication, I think, that's going to be helpful when you think about matching independent pieces together. So I've changed it here a little bit for this next one, okay? So an exam contains 5 true-false questions and 4 multiple-choice questions. Each multiple-choice question has 4 choices. Count the number of ways the exam can be answered. So again, if you wanted to, you could think about like blanks. So 5 true, false, 4 multiple choice. Now you're going to have to decide what you're going to do with these calculations. Like, I hope that really quick you're saying, okay, this one is 2 to the 5th for the true, false. This one is going to be 4 to the 4th, right? 4 choices, right? That's just the same thing we just did. Should I add those numbers or multiply those numbers? See if you can work that out. Come up with a reason for me of, should I add Or should I multiply? Should I add or should I multiply? Mm-hmm. Okay, so what is it? So 2 to the 5th, 4 to the 4th, add, multiply. Votes for add. And we're going to add those two numbers together. Votes for multiply. Ann and Colin, you didn't vote. What if I said it this way? Is this a and or an or? Are you given the choice to do either the 5 multiple choice questions or the 4 multiple choice or the 5 true false? Or are you doing both sets? It actually is going to be multiply. Now, so let me say another reason why. This is why we're doing it, right? So that we can think this through. How about this? So if we answer, like let's suppose we weren't prepared for this at all, and we just go, I'm just going to say true for the first 5. Okay? Now, this next blank, don't we have 4 choices that we could put in there? Like that's what it says, right? A, B, C, D. Okay? So do you notice that if I would just stop the test right then, like let's say we don't have these other 3 questions right now. Okay? So if I answered all true, do you notice that I have 4 options in that moment to finish this test or quiz? But if I had answered all false, don't I also have 4 options? I get 4 options again. Or if I answer false, true, 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 false, isn't there 4 options again? How does that justify multiplication? Can you say that in words for me? Maybe think about the tree diagram. Like that's another justification for it. So I want to hear a conversation. Why multiply? We're going to add sometimes, so you want to keep it straight. Don't think, okay, it's always multiply. Got to be a reason. So you decided your own conversation to have right now? Well, you didn't try though either. Okay, that's fair. So let me say it differently. So if there were only 5 true false questions, how many different tests could I fill out? Right? So if I had a sheet of paper, right? Like how many different submissions are possible with 5 true false questions? 2 to the 5th, which is 32. So I would need 32 tests, and if I would fill out all 32 tests with one of the combinations, one of those would be the right answers for the test, right? Okay. So if I add one multiple choice question, why is there 128 tests now to correspond to the possible answer. It's not plus 4. There's not 4 more. There's not 36 tests that are possible. There's times 4, 128. Can you say why? Annalise, why? Yes. Did you hear that phrasing? For each test, so each of the 32, I now need 4 more for each of those, right? So if I would say true, 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 I now need 4 more pieces of paper to fill out all the combinations. So there could be 4 trues, A. All trues, not 4 trues, 5 trues. 5 trues, A. 5 trues, B. 5 trues, C. 5 trues, D. But then for another of the 32 combinations, wouldn't I get 4 more as well? This is a lot like sandwiches, soups, and drinks, isn't it? That if there's 32 ways I could fill out the true false, and there's 4 to the 4th ways I could figure out the multiple choice, any of the true false could be paired with any of the multiple choice. So just like when we multiplied in that tree diagram, it's multiply here. Because you're filling out the true false and you're filling out the multiple choice. So maybe take 30 seconds. Is there something that I said that you should include in your notes to help you realize the multiply piece? I like the way Annalise just said that, right? Like for each of those has 4 options. Each of the first options have 4 options, which is why it's multiply. Anybody want to ask a clarify question? Carson, does that help with what I'm trying to draw there? Let me say one other thing and then we'll go on. Isn't the multiple choice questions also independent from the true false questions? Right? Like they're independent, so shouldn't we multiply then those values? It's that same thought. Okay? All right, let's look at how this can change and do something a little bit different. Again, thinking about the notion of ways. Let's do this one, a little different. In a race of 7 people, how many ways can first, second, and third be awarded? So there just happens to be 7 of you around the table. So we're going to set up a sprint in the hallway. Who's going to win? So how many ways can we award first place, second place, third place? Think about it maybe as an extension of the multiple choice true false. Okay? So, you done writing? So maybe think of 3 blanks, right? So 3 blanks, 3 positions. So we're gonna, first place, how many of you could get first? Not that you're likely to get first, like maybe there's different things that could happen, but if I'm awarding first place, how many different names could I write down? 7. So is this 7 cubed? I mean, that's what we did a minute ago, but that doesn't make sense here. Okay, what are you thinking? You said no. You shook your head no. Yeah, the options are reducing, right? Like, so you don't get to be first, second, and third place. So that means that this answer is actually 7, 6, and 5. And would this be an example of multiply or add? It would be multiply. So 7, 6, 5. So we have 7 ways to do first place, 6 ways to do second, 5 ways to do third. 210? 210 ways. This has a name. This is something called a permutation. We're going to see some more examples of that in a second, okay? But it has a name called a permutation. Maybe we should do that right now, just before I move too far away from it. If you take your calculators for me. And you actually have to type in the 7 first. So type 7, and then what we're wanting to do is type this. It'll say NPR, and then we're going to type 3. Okay, so NPR is in the stats menu, which is somewhere in the middle. Yes, the stat button there in the middle. And under, actually it's not there. Maybe it's in the math menu. Sorry, it's the math menu. Probability, NPR. So 7 choose, or 7 permutation 3. So your calculator might show this, or it might show this, but it should have said 210. Did it? Okay. Now, what I want you to put next to this is some idea that the order matters. The order matters. So what we mean by that is that ABC is different. So the event of A, then B, then C is different than the event of C, B, A. Okay? So a permutation counts both of these. It counts both. So for us, it matters if you were first place or third place. That's a different calculation. That's a different arrangement of the 7 of you in a sprint in the hallway, right? So we want to count that as different. So the permutation counts it as different. Okay. So I want to give another example of a permutation, something that let's do this first. Wait, any questions on that before I slide away from it? Okay. So it's counting both of these, it counts these as different. All right, so suppose we are going to, so a club is going to vote for president, vice president, secretary, and treasurer. There are 40 people in the club. How many ways can the officers be selected? So there's 40 people. So again, this should conjure an idea of permutation. What about this is order matters? So this is a permutation. What about this is the idea that the order matters? What do you see in the question? Talk to me. Is everything interchangeable in terms of the outcome? So if I think of 4 people, so if 4 of you are selected, if I say the 4 of you are the officers for the club, are they perfectly interchangeable? Why not? And why not? Why are they not interchangeable? Yes. Okay, we definitely can't have one person be all 4 positions. Okay? So what if I say, the 4 of you right here are the officers? Would the club run the same, or do they have the same pool of officers no matter how I would order the 4 of them? So in other words, is it different if Annalise is president or Annalise is treasurer? Is that different? Yes? Yeah, that definitely is different. So we don't want to we don't want to not count that. So in other words, if I would have person A, B, C, D, okay, so person A, person B, person C, person D. If I'm writing this down and thinking that the first name is president, the second name is vice president, then we have the secretary, then we have the treasurer. The arrangement of A, B, C, D is not the same as B, C, D, A. That we want to count these as different options. So that's why it's permutation. Okay? So for us, it would be 40 NPR. And now, so really what we're doing here is this is really the total number of people. So this is the total number. It's a permutation. So this decision is made by we want to count the rearrangements. Okay. And then this is the number that we're selecting. So we are selecting, in this case, so the number selected. The number selected here is 4. So 40 NPR 4. Now you definitely can type this in your calculator. The number gets a little big. There's a lot of ways that this can happen. So what's that answer? Colin, you want to tell me when you get that? $2,193,316. 60. Did you get the same thing? Okay. It's a lot of ways, right? Because we're counting A, B, C, D and also B, C, D, A. In fact, we actually know how many ways that happens. So if I pick 4 people, so listen to this question. So there's my 4 people. How many ways can I order those letters? So if I have the letters A, B, C, D, how many ways could I rearrange them and go, okay, because B, C, D, A is 1. I could do like C, D, B, A. I could do A, C, D, B. I'm just randomly putting, this is a terrible strategy to find them. So how could I get all of these? Give me an idea. How do I get all the ways I could do this? We actually already did a question like this. How many letters could I choose to write down first? So in these 4 spots, how many letters can I choose right now? 4, yep. How many next? 3, then 2, then 1. Shall I add or multiply? Multiply. So that means that there's actually 24 of these, right? So as soon as I pick 4 people, there's 24 ways that I could rearrange those 4 people and get different sets of officers. Okay? Which is why this number gets so big, because as soon as I pick 4 names out of the group of 40, I get like 24 more options just because they could be any of the different officers. So that's why the number gets large here very quickly. In some ways, isn't it like pairing the multiple choice with the true false? Like once I get the true false figured out, then we said, oh, there are 4 options for each of those. There's 24 options every time I find 4 names. Okay. So here's the contrast. Ready? Suppose over Christmas break you decide to read 3 books from a list of 7 books. How many ways can you do that? Already said this one's different. I want to read 3 books from a list of 7 books. So think about on the bookshelf is these 7 books. A, B, C, D, E, F, G. There's my 7 books. I want to read 3 of them. How many ways can I do that? This is not a permutation. This is actually something we're going to call a combination, which is what, Alyssa, you were trying to come up with a minute ago. It's a combination. You know, I said for the permutation that the order matters, that coming in first place is different than coming in second, which is different in third. Or becoming the officers, like if I'm president versus treasurer, then that's different. Why is that not true here? Why is it here that ABC, so in this problem, books ABC is the same as books BAC? That these are actually the same for this problem. Why? Yeah. You still read them. So we're really looking at the end of the break. What 3 books did you read? Does it matter the order that you would say them in? Is that different? It really isn't, right? Because we're just really saying what are the 3 options that you're choosing out of the 7. Okay, so how about this? Like, here's one approach we have. So if I would just say, and approach this problem with the 3 blanks like we were doing a second ago. So how many books could you decide to read first? Not a trick question. It's 7. Okay, but now you've read one. So how many books can you read second? 6. How many can you read third? 5. But we have actually double counted. So this answer of 210, which is actually the answer we had a second ago, right? Yes, 37, 210, is too big for this problem. Because we counted these 2 differently over here. You with me? That if I say I had 7 options here, couldn't the first option have been A? And then the second option could have been B, and the third option could have been C, right? Didn't I count that in this group of 210? But didn't I actually also count BAC? And didn't I actually also count ACB? And didn't I also count CBA? Do you see all the duplicates? So if I chose to read the first 3 books on the shelf, how many ways could I write down those 3 books? So books ABC, how many ways could I write them down? So one way is ABC. The second way is ACB. I could read BAC. I could read BCA. How many are there? Talk to me. How many ways can I read those 3 books? 6 is the right answer. How'd you get that? There's an extra, sorry. I didn't hear the last thing you said. Oh, so you're just thinking of the options here, so like CBA, CAB? And we've actually accounted for them all. Do you notice that that's the same answer as saying there's 3 options? Do you notice that there's 3 options to write down first? Which would leave 2 options to write down second, which forces, like once you name the first 2, aren't you forced to write this one down? Do you see that that's 6? So that means this answer is not 210. What is it? Take a minute at the table, come up with it. So how many ways can we read 3 books from a list of 7? If we start with the number 210, we double counted. It's too big. We counted all of those as separate, but they're all the same. It's the same 3 books. So what are you going to do with the number 210? See if somebody has an idea. Open your mouths, speak to one another. Bella, what do you want to do? Why? So why not subtract it by 6? Yes, we'd actually still be double counting. Like, aren't there other books on the shelf here I could have chosen, right? I could have chosen D, E, F, but wouldn't there be 6 ways that I could read those 3 books? But couldn't I have done book A, B, and G? Aren't there 6 ways that I could read those books, right? I could which one I read first, second, third, but if we don't care about that. So every combination here of 3 letters produces 6 duplicates. So we need to divide out the duplicates. So that's actually how I'd say this. We're dividing out the duplicates. Now, your calculator can actually do this. If you go back to that probability menu, you should see an NCR. So that would be, for this question, we have 7 books. So it would be 7 NCR3 or 7 combination 3. And it should give you this answer, 210 divided by 6, is it? So 35. Who actually uses their locker? Any of you use your locker? Who knows their locker combination? Seriously? No one even knows your locker? You don't even know where it is. That's interesting. Have you ever used your locker? Do you use a gym locker? Okay, so your gym locker has a padlock on it, right? So it should, or somebody will steal your money or your calculator and pawn it. So, do you know your combination for your locker? Okay. Let's just say that it's the numbers 1 through 49 on the padlock. Okay. So since none of you know, unless you're going to throw out a number. Okay. I thought you were going to tell me that it was a. So, do you know the highest number on the lock? Okay, we're going to say it's 49. Okay. So 1 through 49. No, it's not. Maybe 50. It's around. Yeah, it stops. You want to go 60? We'll say 60. No, it just makes it a little bigger with the final answer. So now when we think about the locker, like I know that we call it a combination lock, but don't use that to try to answer this question because our language, like you've probably never heard, oh, that's a permutation, right? Like people will use the word combination to mean both combination and permutation, so don't try to answer based on it's a combination lock. But I'm wondering, is a padlock, is it a combination or is it a permutation? And so let's say that there are 3 numbers. So we have to enter 3 numbers and they can't repeat. Okay? And that's usually true with locks. Like some locks would let you repeat numbers, but it actually makes it a lot more insecure. But let's just say they can't repeat. Okay? So, first question. So combination or permutation? Make an argument at the table, decide how you're going to vote, and then we're going to find the number of ways to assign a code to a padlock. Notice that if you can't answer the first question, you'll never get the second one right because they're different answers. So make an argument, then solve it. So the real question is, can you put the code in any order and open the padlock? Like, can you? So is 5, 10, 25 the same as 25, 10, 5? Is that a different combination? If the difference, now I said combination, but because that's what we call it, so is it a permutation lock or is it a combination lock? It's actually a permutation lock. So if you can get that to catch, like you can start telling people, asking people, do you know your permutation for your locker? It's a permutation, okay? So if there's 60 numbers, actually, yes, so 60 numbers, 1 through 60. So this should just be 60 times 59 times 58. Now, you can also do on your calculator the 60 permutation, 60 NPR 3, because we're choosing 3 numbers. But it should be this answer here. Okay. So, new question, and then I think we'll finish with this one. Okay. Suppose we're selecting our steering committee or committee for class night. Okay. So these are going to be people that get together. They're going to do work. They're going to do everything that's required to make sure that the class night goes off. But there are no positions. We're going to select 6 people from the group of 20 interested. So for example, this could be something like we have people vote. The top 6 vote getters are selected to the committee. How many ways can this happen? Now, again, that first question that we want to ask ourselves is, does a rearrangement mean a different way? Or is it the same the way that I'm phrasing it? So if 6 of you get selected and I say your names in different orders, does that change the group? The same thing's actually true when you think of homecoming, a homecoming court, and you vote, right? And we list off the people. Does saying their names in a different order mean a different court? So once you've decided whether this is a permutation or combination, then you should be able to come up with an answer. Look at your neighbor's paper, see if they did the same thing. Somebody look at Colin's paper. Is he right, Annalise? Combination, permutation? It's definitely a combination. Why? Say that again. The order doesn't matter. The order I would say the names doesn't have any difference, right? It's still the same 6 people that are going to be doing the work on it, right? So there is not positions. There's not a hierarchy being set here. That would be the difference of officers, right? Officers definitely has a structure to it. This doesn't. So this should just be 20, choose 6. So what's that answer? Annalise, what was it? What would this be? I'm going to change the committee size to 14. What is it? It's actually the same. Does that feel weird? That I'm choosing more people, but I got the same answer. So I wonder if I could illustrate that in the class, just looking at the 7 of you, okay? Ready? So what if I'm going to say, I'm going to pick 3 of you. So the 3 of you, could you go down to the main office and do something, get something for me and bring it back? Okay, so the 3 of you. Go to the office. Get that for me. Bring that back, please. Okay. So we could calculate the number of ways that can happen. Why is choosing 3 out of the 7 of you the same as choosing 4 out of the 7 of you? What do you mean? Well, I'm going to make the 4 of you stay. So the 4 of you are going to stay, the 3 of them are going to go. So why is choosing 3 of them to go the same as if I change my mind, I'm going to say 4 people are going to go and 3 people are going to stay? Why would that be the same? Why is choosing 4 out of 7 same as choosing 3 out of 7? Yes? Okay, so now I could get a bigger or smaller answer if I say select. So let's try this. So what if out of the 20 people I say I'm going to pick 19? Does that number go up or down? It went down. So so it could change, but you're onto something of thinking about the choice. There's something really unique about this choice. So why is choosing 6 the same as choosing 14 in a group of 20? Can you see it? Let's go back to this example. So if I pick the 3 of them and say go to the office, didn't I really pick 4 of you? Let me say that again. If I pick 3 of you and say go to the office, didn't I also pick 4 of you at the same time? Yes. What are you thinking? Yes, 6 and 14 add to 20. So if I choose 3 of you, didn't I not choose 4 of you? And the ways I could not choose 4 of you is the same as the ways I could choose 3 of you. So let me say another way. By choosing a group of 3, didn't I force a group of 4? So choosing 3 and 4 out of a group of 7 must be the same. So choosing 14 or 6 out of a group of 20 is the same. So this is actually then always true. So if I would say like NCR must always be the same as NC N minus R. Just looking at this example, right? 20 and 6. So if I take 20 minus 6 and make that 14, they have to be the same. Now, last connection and then I'm done. This is actually related to something you've seen before. What is this? Do you know? I mean, I'm pretty sure you know. Yes, there it is. Pascal's triangle. So 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 5. I'm sorry, 10, 10, 5, 1. Do you notice the symmetry in this? Right, 1, 6, 15, 20, 15, 6, 1. Isn't the left side actually always the same as the right side? And what you probably didn't realize at the time is that every entry here is actually a combination. Every entry here is actually a combination. So if I would call this, look at, let's say, this number. So if I would say 4, oh, that number is maybe not a great number to pick because I'm going to choose this one. Okay, so do this for me. What is 5 choose 1? What is it? It's 5. What is 5 choose 4? It's got to be what? It's got to be 5. That's actually this 5 here. So this is going to correspond with the value of 1, and then this must be actually 5 choose 2. This 10 right here. So this is actually 5 choose 2. This would be 5 choose 3. This would be 5 choose 4. This must be 5 choose 5. So if I would say, okay, I'm going to send all 7 of you to the office, how many ways can I do that? Isn't it 1? Right? You all got to go, right? There's no other option. There's no way to leave someone behind. But here's then the curious thing. How many ways can I choose none of you to go to the office? It's really 1, right? All of you stay. So this must be 5 choose 0, which is, there's 1 way to do that. Okay, so I choose none of you go to the office, you all stay. So this is the start of 8.1. We're going to look at some more examples tomorrow, but you definitely should be starting the My Math Lab. The key thought today is, 1, you have the fundamental accounting principle. Can you multiply things together and get a right answer? But then we have to start separating, does a rearrangement count or not? Permutation, combination. So please start that. Come tomorrow with questions. Have a good rest of your day. See ya.